Today we're going to talk about recurrence relations, which is a first step towards developing mathematical models for the performance of computer programs, as we saw when we covered the analysis of quicksort in the last lecture. To begin, we're going to look at the idea of using the computer to compute values of recurrence relations. This is very important for us as, unlike many other mathematical disciplines, we have the ability to be able to quickly check our answers and maybe develop hypotheses about the answers that we're looking for. But first of all, what is a recurrence? Well, it's simply defined. It's an equation that defines a sequence recursively. That's easily understood by computer scientists, and just as a simple example, here's the Fibonacci numbers recurrence, which is familiar to mathematicians as well. The recurrence relation is f sub n equals f sub n minus 1 plus f sub n minus 2. So that's defined recursively. Each term in the sequence is defined in terms of previous terms in the sequence. But it's very important, as every programmer knows, in a recursive program you need to specify the initial conditions. Also, in a recurrence relation, you need to carefully specify initial conditions and make sure that things are defined for all values of n. In the case of the Fibonacci numbers, we define f0 to be 0 and f1 to be 1, and then insist that the equation hold for n greater than or equal to 2. So f sub 2 is 0 plus 1 is 1, f sub 3 is 1 plus 1 is 2, and so forth. We get each term in the sequence by adding the previous 2. So that's an example of a recurrence relation. So now the question that naturally comes up is, if we're given the recurrence relation, can we come up with a simple formula for describing fn as a function of n, as a simple function of n? That's the kind of question that we're going to be addressing. Now, as we saw in the last lecture, recurrences directly model costs in programs. For example, we talked about quicksort, and it's a much more complicated recurrence, but it still has the same property that every term in the sequence, in this case the sequence defines the running time of quicksort, or the number of compares taken by quicksort. Every term in the sequence is defined in terms of earlier terms in the sequence. In this case, the result is not integers, and you can work out that C0 is 0 as specified, C1 is 2, and so forth. That's the number of comparisons used by quicksort to sort n elements. And we derive the recurrence from the program. It's a mathematical model of the running time of the program, specifically the number of compares taken to sort a randomly ordered sequence of array of n distinct elements. Now, a common sense rule anytime you're faced with a recurrence nowadays is just to use the computer to compute values to see if you can understand what the values are and what's going on. It's even better to do that before doing the math, as it might tell you something that might be difficult to discover with math. And it's so easy to do. So first thing you might say is, why not use a recursive program? Well, we teach now in every elementary programming course that you don't want to do this. It's a very bad idea to try to compute values of a recurrence like this with a recursive program because it takes exponential time. That is, to compute f of 50, we have to compute 49 and 48. To compute 49, 48, and 47, and so forth. And if you look at this table, you'll see that we're recomputing values all the time. F of 48 twice, f of 47 3 times, f of 46 5 times, and so forth. Actually, it takes exponential time to compute this, so it's not going to complete even for F50. It's much, much too slow. So it would be nice to think about using a recursive program, but we don't do that in practice. Instead, what we do is save all the values in an array, and so we'll need an array entry for every value that we want to compute, but nowadays that's no problem. So in this case, if you want to compute f of 50, we make an array of size 51, set the first two values according to the initial conditions, and then simply go ahead and compute for every value in the sequence, its value from the previous two values. So that's a common sense way to deal with any recurrence, just use an array. Now, what we'll do is maybe a little more complete, and I don't want to make this a course on modern programming techniques, but I might as well use modern code so that we can leverage off of all the code that we've developed for our algorithms in Introduction to Programming in Java courses. So if you go to the Algorithms 4th edition book site, you'll see a To Get Started link that you can go ahead and use to download some standard library packages that are available for average programmers to write these kinds of programs using a modern model. This is not required, but many people will be familiar with this model, so it's the one that I'm going to use for the code that I cover in this course. And this code is easily translated to other environments and languages, so I'm not going to dwell on that. Nowadays, in a modern approach, here's this code that goes ahead and fills up an array with of size n or size max n with the Fibonacci numbers. But this is a modern approach where we use a data type, and the client program will go ahead and build this array with a constructor and then ask for values out of the array. Again, this is not the place to talk about details of programming with data types, but this is a very straightforward way to approach this problem. And the reason that we use it is that we can reuse code or write code that we can use for different sequences just by saying that the only way that we're going to evaluate with or deal with what the sequence is to use this eval function to get out a particular value. And then we can write code that will print out values for any sequence. So this code, for example. Again, in this case, with this code, there's not that much code. We want to get the first 15 Fibonacci numbers that prints it out for us. And you can, in your own programming environment, do whatever you want to get that result, and that's an exercise worth doing. Now, more interesting, let's look at the quicksort recurrence. Now remember, we did some algebra to show that we can make the quicksort recurrence a very simple linear recurrence rather than the one involving the sum. And so this is the corresponding code for the quicksort recurrence. Using that version of the recurrence, we can, in the constructor, create an array, fill it up with the first n values just using that recurrence. So it's just dividing by n, and then eval will give us the value of that recurrence. So the same code will print out the first 15 values of the quicksort sequence in that way. So that's a good first start, so we can get some idea of what these numbers are. But actually, often what we want to do, and I'll have plenty of examples, some examples in this lecture, is we just want to plot the initial values. We want to draw the curve to get some idea. So this code here uses our standard library for drawing things within a window on your computer to do the plot. And I'll have some examples later on that use this kind of code to just draw the value of each recurrence for n on the x-axis and the value of the recurrence on the y-axis scaled to the largest value. That's what this code does. So in the case of quicksort, if we use a call on this show method instead of printing out the values, then you get the curve like that, which is the curve for n log n in this case. So that type of a code is a good starting point, and if you don't want to use my Java code, it's definitely worthwhile for you to use whatever programming environment you're comfortable with to be sure that you can compute values of any recurrence efficiently, and also to be able to develop plots like this. And you'll get a good feeling for why we want to do that in just a minute. So that's computing values of a recurrence.